Every year, several hundred million cubic meters of sediment, which are dredged from ports, harbors, and waterways, is disposed of in open water. Disposal of dredged material can negatively impact marine ecosystems through entrainment, sedimentation, and increases in suspended sediment concentrations. Now, why do I tell you this? Because my objective with this presentation is to introduce a novel method to reduce the turbidity and mass loss as a result of dumping sedimentary materials in the water environment. My name is Mahsa Janati, and today I'm going to tell you how dividing a total mass of dredging materials into two equal portions and releasing them with a certain distance into the water environment will lead to reduce the negative impacts of dredging activities. Particle cloud can be formed when a volume of sand particles is released from a nozzle into ambient water. An instantaneous releasing of sedimentary materials into the ocean occurs in two main engineering applications: land reclamation and dredging activities. Land reclamation is discharging of sediments in designated areas for construction of artificial islands. To prepare the artificial island, which is a massive construction work, a large amount of sand is required. The examples of artificial islands include the Palm Jumeirah Beach in Dubai and Kansai Port in Japan. Dredging activities include releasing dredged materials into the aquatic environment, which leads to water quality concerns. Remaining sediments in water column causes adverse effects on marine ecosystems, which means that it may interfere with the fish pathway or other marine life ecosystems. In order to combat the adverse effects of dredging materials in water and deposit the materials exactly in designated areas in land reclamation, we need to understand the mechanism of sand dispersion in water. Only by following the mechanism we can find a way to make the best decision in situations in which sediments need to be dumped into the ocean. The first objective of this study is understanding of the mechanism of sand dispersion in water. The second objective is obtaining the physical properties of the cloud, and the third objective is investigating the effect of releasing sand particles in form of twin particle clouds in stagnant water and compare the results with the corresponding single particle cloud. The main focus of our study is the experimental modeling of releasing single and twin particle clouds in stagnant water. There are three phases in the particle cloud formation. The initial acceleration phase, within which the particle cloud accelerates as a solid body until it reaches to a turbulent condition. The self-preserving or turbulent thermal phase, where the vortex ring is formed inside the cloud. And finally, the third phase or particle settling phase, in which sand particles detached from the entrained fluid and descend individually at their settling velocities. In this slide, we have prepared a schematic of our experimental setup. As you can see, the nozzles are attached to a board here, and then the particle clouds released through these nozzles into the water environment. Also here we have prepared a video of twin particle clouds. As you can see, the clouds experience the three mentioned phases of formation. Here is a table in which you can see the four main aspect ratios for single particle clouds. And regarding the twin particle clouds, we divided those masses into two equal portions to see what will happen during this test. Also here you can see the distance, the non-dimensional distance between two nozzles, which is different based on their test. This image shows the time evolution of twin and single particle clouds with the same aspect ratio of 19.4 in different non-dimensional time. As you can see in this part, the initial acceleration phase in single particle clouds and twin particle clouds are somehow the same. But going further on, as you can see in here, the two particle clouds are drawn toward each other, and in here they started to interact and mix with each other. The most important factor of dividing the mass into two parts is that the trailing part of the cloud in the water column can be diminished faster in twin particle clouds. As a result, the risk of turbidity and mass loss, which can cause severe problems in the water environment, can be reduced. Another benefit of splitting the total mass of sand particles into two parts is that the mixing will be enhanced and the dilution will be improved. This figure shows the single and twin particle cloud development in the different phases of motion. Here in the first column, we have 1.6 grams of sand particles releasing from one nozzle into the water environment. And we want to compare this with the 2-3 grams of sand particles releasing from two nozzles in different source separation. The twin clouds with very close distances evolve in a dense and highly symmetric shape that looks like a sphere with sparse trailing sections. However, by increasing the source separations, the two clouds are not fully merged even in the dispersive phase, and they only have a very small attraction toward each other. Another aspect of releasing from two nozzles is when we increase the source separations, the width of the result cloud will be increased. So this can be helpful in the case that we want to nourish a vast area of aquatic environment with nutritional substances. In addition to width and length of the particle clouds, another important parameter in the particle cloud formation is the frontal velocity of the cloud. This figure shows the variations of cloud frontal velocity aligned with the water depth for two particle clouds with the aspect ratio of 9.7 and source separation of 2.5. The results of proposed equation by Moghadaripour et al. In 2017 also added to this plot to make a comparison. So as can be seen here, from the beginning of the releasing point until z equals to 20 centimeters, there are some instabilities in frontal velocity of the cloud, which is because of the interaction and the first collision of these two particle clouds. After 20 centimeters, the results are pretty compatible with each other. When two particle clouds are discharged at a very close distance, they have a common ambient between them. So each of them tries to draw the common ambient inside the cloud. So because of this, we have this fluctuation. This figure shows the variations of centerline velocity of the cloud on the main particle cloud and two individual side clouds. As you can see, the centerline velocity of the main particle cloud is about 30% higher than the two individual clouds. This, the velocity inside the clouds obtained from PivLab in MATLAB software. In conclusion, we have listed some most important findings of our studies. First of all, the length of twin particle clouds were 36% reduced compared to the corresponding single particle clouds. Twin particle clouds with small source separations, such as 2.5, have the smallest cloud width amongst other source separations, as small as a single particle cloud width. And for source separation greater than 7.5, increasing source separation by 50% make the clouds width larger by approximately 15 to 20%, which may be useful in particular dredging activities where a designated area is defined to dump dredged materials. Thank you for your attention.